All right, so in this video, we're going to talk about radiation shielding and how to measure shielding. And this builds on what we've learned so far, which is the risks that are potentially associated with radiation exposure. So the concept here is that you want to keep the doses in the ALARA realm. So that means as low as reasonably achievable, ALARA. And that's the concept behind shielding and protection. And so I'm going to go through this as an example using radiation therapy. So in other words, building a bunker or a vault around a radiation linear accelerator device. But a lot of this applies more generally. So it would apply to, for example, an HDR therapy suite. There are also calculations that you can do for diagnostic radiology, for nuclear medicine. And these are slightly different, but the basic concepts are still there. And then at the end of this, I'm going to talk about detectors, and in particular devices that you use for shielding surveys and for other ways of detecting radiation, like, for example, a seed in brachytherapy. All right, here we go. So the most important report for this is NCRP 151. It's a very readable report, and I suggest you go through it. We'll start with an example. So here's a LINAC room, and the LINAC is there in the middle. And we want to calculate the shielding that's needed. So I'm going to build a little area. It's a control desk. Let's say this is where the therapists work. And they're radiation workers, remember. Here's an office. Not a great design, really, but there it is. So the goal here is to calculate the barrier thickness. So the thickness between the walls, maybe the wall between the office or the wall between the control area. And they need to be thick enough in order to keep the exposures down below the permitted levels. So we're going to use the NCRP 151 limits. That's going to define the levels that are acceptable. And it uses a principle called ALARA, as low as reasonably allowable. So this is a very important concept, and the report defines for you what is reasonable, what are the limits. So first we're going to consider a controlled area, like the control console. That's an area where you've got radiation workers, people with badges, where the area is controlled. NCRP 151 says in this area we should shield so that we get less than 1/10 of the maximum permissible dose. That's what they mean by as low as reasonably allowable. That's how they define it for this controlled area. So this is 1/10, and then you remember the maximum permissible dose. It's 50 millisieverts per year, right? So I multiply this out, I get 5 millisieverts per year. Now it's more usual in this case to quote these as the millisieverts per week. So let's do that. We're going to divide by 50 because there's about 50 weeks in a year. And so in the end, we get 0.1 millisieverts per week. So that's the limit for this controlled area, according to this report. You want to shield for this. All right, now let's consider what happens in a public area. What is the shielding requirement there? So this is an area where it's not a radiation worker, it's a general public. So the report says that in this area, you should shield for just the maximum permissible dose. So not 1/10 of the maximum permissible dose. And that's just because if you shielded for 1/10 of the limit, the shielding would just be extremely thick. So it's not reasonable. So you do the maximum permissible dose, you remember that value, look it up, it's 1 millisievert in a year. And then if we express that per week, this is the value we get, 0.02 millisieverts per week. This is the number you shield for in a public area in a week. So let me just put these in a little box and save them. Oh, and by the way, you typically will shield to 1 foot from the wall, which is where you do that. So I'm going to walk through how to calculate this. You start first with the workload, W. That's how many gray per week the LINAC puts out. You take the usage. That's how often the beam points at a particular barrier. And then you take T, the occupancy factor, of the region that you're in, so for the office or whatever you're shielding to. So what are some occupancy factors? For the office is 1 they use. Somebody's always there. Exam room, its suggestion is to use a half, according to NCRP 151. A hallway, you use a 5th, and there are some other values in the report. And then we multiply this by B. So the B factor is the barrier transmission. What fraction of radiation is transmitted through the barrier? So all these factors together, then, you divide by the distance squared. So that because there's a 1 over r squared fall off as farther you get away. And that total then is P. That's your goal. So after you have designed the right barrier, the P value should be less than or equal to what you want to achieve. Yeah? So typically this equation is written backwards. So let me rewrite it. P d squared over W U T. That's typically how you see it written because you're calculating for B. All right, so now you have all the relevant equations, but I want to acknowledge that there's a lot of symbols here and it's a little confusing. So to understand it better, we are going to work through an example. And what we're going to do the example for is to calculate the thickness, barrier thickness required to properly shield for this office area at the point X. So first of all, let me explain the geometry here. I've drawn out these little green areas. So what this is indicating is the fact that the linear accelerator can point to either of these walls as it rotates around. It could also point down towards the floor or up towards the ceiling. When it points towards the wall, towards the office, it's going to irradiate this green shaded area here. So this is the area you would have to shield. And this is for a primary shield, so that where the beam points directly at the wall. To figure out how big this area is, you just project the maximum field size of the linear accelerator onto the wall. So typically 40 by 40 centimeters. And then you have to look along the diagonal, and that's at isocenter, and then you project it onto the wall. And you can figure that out. Now we're going to use the equation down here to calculate B. And B is the percent transmission through the wall. And so to start, we need to know what all these factors are. I told you what D is, and we have to figure out what P is. So P is the goal, the shielding goal, what the limit is. So remember from last time, our goal, as I defined it, was to be less than 0.02 millisieverts per week. All right, and this is the goal for a public area, an uncontrolled area. So we're going to assume that this office is somebody who's not a radiation worker. So like this is not a great design, but let's bear with me here. All right, so now I'm writing out the equation. B equals 0.02 times 5 squared. I'm going to use 5 meters, and I'm going to use 750 gray per week as the unit. And then U, I'm going to use 0.25. Okay, so let me explain that. Why is it 0.25? I'm saying that the beam can point to that wall a quarter of the time, because it can point up a quarter of the time, right quarter of the time, left a quarter of the time, down a quarter of the time. It's just an approximation. That's the use factor. Okay, and then finally I'm going to use T equals 1. T is the occupancy factor. What fraction of the time is this room occupied? I'm going to say it's occupied all the time. It's an office. And then plug and chug in the numbers, and here's what you get. So this is the transmission, fractional transmission through that wall from the LINAC operating at 750 gray per week. All right, so you will say, oh, well and good, Dr. Ford, but how thick of concrete do I have to pour to shield this LINAC? So let's do that. Let's calculate the thickness. We're almost there. So thickness we're going to express in terms of the number of 10th value layers, number of TVLs. And that equation you can write like this, log base 10 of B. And hopefully that's obvious if you just think about it, because you know the equation 1/10 to the number of TVLs equals B. Take the logarithm of both sides, minus sign comes down, and you get this equation. And then now if you plug the numbers in from above, plug the value in for B, here's what you get. Okay, but I still don't know how thick to pour the concrete, but we're really close because now we know we can go and look up how thick a TVL is. So we pull up NCRP 151 report, look in this Appendix B, and you find the energy of your linac. Let's say we're using an 18 MV linac, and let's say we're using concrete as a material for shielding. And then we would know from that that the first TVL was 45 centimeters here, and the TVLs after that were 43 centimeters. And so now I can plug this in. So I write that the first TVL is 45 cm, and then I'm left with 1.57 TVLs, and each of those is going to be 43 cm like we saw on the table, right? And when I multiply this all out and add it up, here's the number I get, is 112.5 centimeters. So about a meter thick, which is 3.7 feet. And that's the thickness of concrete you have to pour. Okay, now I'd just like to add one thing before we wrap up, which is that this is a primary barrier, so the beam can point directly at this area. And so the barrier thickness is very thick. Typically, in a primary barrier, you might not use just concrete. You might use some combination of concrete and steel to make it thinner. But you can do a calculation for that too. So that was the example. What we calculated here was primary radiation. So these are beams that are coming directly out of the linac, and it can point in different directions as the linac rotates. It can point up and down too. So that's one form of shielding, primary radiation. And here's the formula, which is what I gave for the barrier thickness for the design goal P. But there are other kind of radiation too. There's leakage. That's leakage through the head of the linac and coming through the walls. Okay? And it comes in all directions through the barriers. And the formula is very similar. So the design goal P, the distance, and the use factors. But the use factor is 1 because the beam is always pointing at every wall for leakage. So leakage, kind of by design, is less than 0.1% of the workload of the linac, so you can use that too. And so you can rewrite it like this. This is usually how it's written. So 0.1%, 0.001 times W times T. Okay, now there's a third type of radiation. So you're radiating a patient, and radiation scatters off the patient and then comes through the barrier. So that's scatter radiation. The formula is complicated, so I'm not really going to get into it. But one of the principles in shielding is typically that in a linac, if you shield for leakage, then you're also usually okay for scatter shielding. And then a final important requirement for all shielding calculations has to do with the instantaneous dose rate that comes out. And the regulations here say that the dose rate has to be less than 2 millirem in any 1 hour. And that's often the limit that you run into when you do shielding calculations. So now I'd like to make some observations that are particular to shielding for neutrons. As you know, beams over an energy of 10 MV will make neutrons, and the considerations for those shielding those are slightly different. So when thinking about shielding for neutrons, you really only need to consider those energies. Lead does not work well. You need a material with a lot of hydrogen because you need the elastic scattering that happens with the hydrogen nucleus. Concrete barriers are usually enough to shield for neutrons, but you have to worry about situations where there's steel. And so doors are one example. There's a problem because there's not a lot of hydrogen in it. So one solution for that is you can use a maze. So that's kind of like a pathway to the door. Or you can make a door of polyethylene, typically with boron in it, because that has a large neutron capture cross-section. And if you do use steel, you want to put it on the outside of the door that's to shield for the capture gammas that are created when the neutrons are absorbed. And then finally, smaller rooms need bigger doors because of the 1/r² effect. The final thing I want to spend a minute talking about are meters. So devices to measure exposure outside of a barrier once you've calculated it and built it, just as a check. Or these meters can also be used, for example, for finding a loose seed or other applications. So there are basically two types of meters. So one is a Geiger-Müller counter. These are extremely sensitive, so they could be used to find a lost seed, for example, but they don't give you a measurement of the exposure in like millirem per hour. They're typically calibrated in count rates, counts per hour. And so you might use this first to find a hot spot, an area where you need to look further. The second type of meter is a survey meter. This is not as sensitive, but it is calibrated for exposure, typically millirem per hour. And you hold it up to a wall, and you can, or wherever, and you can do a reading of those. So these meters come in a variety of different kind of configurations, and you'll see here different detector heads on them. Here is one that has a sodium iodide crystal in it, and you can see that then it's very sensitive to the low energy photons that are emitted, for example, from a brachytherapy seed. So they're good for finding those seeds. All right, so that is the last of these videos on protection and exposure from radiation. And I will leave you with a little bit of further reading and some more background. And I'll see you in the next video.